Here for the mic on. First of all, thank you very much for having me and for the organizers of the workshop. It's a pleasure to be here. A lot of familiar faces. I thought, for the past 15 years, my main research passion and interest has been computer vision. So I thought I'd spend some time sharing with you some thoughts about how can we harness machine learning, in particular computer vision, to enable us to do global discovery at scale. We're in the situation, and Dr. Honey just touched upon this right now, where we have this explosion in amount of data, and we're also in a situation now where conflicts can essentially arise at any moment and without much warning. So this has really challenged us to how do we think about collecting intelligence. And at the same time, this is another thing that's happening right now. We have, I think that Joe Mundy touched upon this last time. We're also in a very exciting moment. There's a lot of challenges associated with being able to collect intelligence at a global scale, but it's also a very exciting moment because of this kind of emergence of commercial space, and I wanted to touch upon that a little bit. But one of the key things that I keep thinking about is, we're in the situation where, our adversaries are continuously now escalating conflicts in these kind of subtle, decentralized ways that are usually only perceptible really when we look at things at a much larger global and temporal scale. So that's where I really feel that is a great insertion point for things like computer vision and machine learning, when we really need to scale out and focus attention of individuals. So as Joe Mundy talked about yesterday, we're also in this very exciting time where now we went from the situation where we had essentially one company that in the commercial space that was imaging about 5 million square miles a day, to now we're in a situation where we have tens of companies that are imaging 200 million square kilometers a day. And there's companies like Planet that are looking at imaging the world once a day, which is incredible. And it's not just the number of pixels. We're also seeing a lot of diversity in the modalities. So this is really exciting because you have things like Anthony Hooks yesterday showed some video from Skybox, and this is fascinating. The first time I started working with this, is like, wow, we have commercial just video from space. We also have other kind of sensors. Also, Joe mentioned synthetic aperture radar. So it's exciting to see these developments. We've seen this explosion in diversity in the spectral space as well. Now, at the same time, of course, we have just the also massive number of uncooperative and non-traditional sources that are just out there. I'm still stunned to think that 400 hours of video are uploaded to YouTube every minute. So it's stunning to me. And a lot of these things have things like geotags, and so the question is, how can we harness these uncooperative, non-traditional sources to help us focus our attention, also focus our kind of more exquisite government-owned assets that are usually just soda straw views? How can we use these uncooperative, non-traditional sources that are out in the open to help us focus our attention? So that's kind of what I wanted to explore a little bit today. Now, we talked about this a little bit yesterday, I think in every presentation a little bit, but as a computer vision community, up until recently, we were in trouble. We really didn't have much to offer. We've been working on this problem for quite a bit, but we didn't have something that was very robust for, say, object detection. And this is surprising sometimes, because you would think that we were sitting on this mountain of data, and in a sense, visual data can be thought of as the biggest of big data, right? You have the 400 hours of video that we just talked about. We have, the 300 million photos that are posted on Facebook each day. In fact, Cisco has a study that shows that close to 90% of all net traffic is soon going to be visual. So you'd think, hey, can't you just brute force this problem? You have all this data, so why are you complaining? So a colleague, Pietro Perona, likes to call this massive images and videos that we have out there, it's just digital dark matter, right? It's just sitting there. No one had even seen most of it. No one knew how to index it or effectively reason about it in any way. So that was the situation we found ourselves in. And of course, the problem really resides, and Rama mentioned this, much more eloquently than I could put it, but essentially it was really a problem of representation. You take an image such as the one that you see over here, it's made up of pixels, right? These lifeless, meaningless numbers. So as he said, we essentially were in this kind of boutique, business where we were doing all our features and our different classifiers. And we were all in this business. So this is where we're trying to go from these low-level numbers to meaning, and this was always the challenge. Now, again, as people mentioned yesterday, these things started to change a little bit. This is a video here of Jan LeCun showing one of his early, convolutional neural nets that essentially is doing, digit recognition. And what was interesting about this is that it's an end-to-end system, right? It's not doing the feature engineering. It just goes from, the data all the way to the labels. So this story has been told a million times, so I don't want to dwell on it too much. But Jan is now a big guy in deep learning. I'm honored that we have Rob Fergus here as well, another eminence in this area. So these people have had a tremendous influence on the field. But you know what? A lot of us did not see this coming, this revolution, and I was really I was very interested in hearing Rama's reflections about how do we as researchers react to that, and what is our way of embracing that. To me it's funny because before my current position, I was actually in a lab that, Jan would visit us all the summers, and he would every single day, tell us, you need to start looking into these deep learning approaches. And here he is. This is a classic picture. He's convincing everyone, try to do this deep learning stuff. And I'm all the way off to the right over here. This is back when I had hair, completely ignoring him and perhaps having a little too much fun in the French countryside, drinking port or something like that. But so the point I want to make is that, I did not see this, the influence of this set of deep learning approaches, come even when I was right in the middle of it, so I was listening to Rama and doing SVMs. Just kidding. But
I think it's okay.
That's right. That's in fact, that's one of the biggest things that most people do. But so at any rate, it really didn't hit me until I was with the rest of the people and seeing, geez, oh my gosh, we see this big jump in our ability to recognize objects. When this method was used for the first time in one of the ImageNet challenges, and of course Anthony I think talked about this really nicely. He added another part to the stool of why now? Why is this happening now? People usually cover there was the massive amount of label data. There's 50,000 people it took to create ImageNet. I was one of those, just as a graduate student, labeling things and contributing. So that was one piece of the puzzle. The other one was compute, right? When now we have these GPUs that are relatively cheap and able to do amazing computations. And I like that you added, Anthony, yesterday. I think we need to acknowledge more often is just the open nature of our community. So I don't have that as of yet. I didn't update my slide after talking to you, but I think that's a great thing to acknowledge. So this created a Cambrian explosion. So you see all these different methods and algorithms that are all using similar DNA of approaches, but they're doing everything from coral reef classification, overhead classification, surveillance. As part of the Maven program, we were recently going out to the valley and just talking to all these different companies, and it's amazing. Under the hood, they're all using the same kind of set of approaches. Very similar, at least. So it's amazing to see that. So there was a diaspora of these ideas that kind of started out in academia and quickly went into industry and national labs. So what's exciting is to see, okay, what can we do with this now for global discovery at scale? So if you can do things like object classification at a reasonable accuracy, we could really imagine now beginning to harness these sources that are fairly noisy and uncooperative. So, things like social media, which I'm excited to hear, it will be a couple talks right after me. If you're talking about the pixels themselves, you could really start to focus attention, right? So now this is, yet another pipe of data, and as Dr. Honey said, we need to be careful if we're introducing yet another problem, actually. So you really need to, what can we do with this that would be of value? And what we're seeing is that you can take this very noisy source, and you could start finding objects and events of interest. And I think Joe Monday said something yesterday that was also resonated very strongly. If you take these detections individually, it could be dangerous sometimes because it's going to make mistakes. So it's interesting to start aggregating these results to do things like indicators and warning to give us kind of a global coverage and start understanding the patterns in some of those detections. So what you're seeing over here is just of different military targets on social media, and using exactly what Rama just mentioned. Sometimes you could bootstrap your method using, this is a classic transfer learning, bootstrap using ImageNet, and then you have some maybe subset of labels that are not as large as ImageNet, but then you could do things like aggregate these detections that might be slightly noisy and provide you some insights from those kind of large-scale data sets. Now, the other thing is we're seeing is a lot of commercial companies are providing things that are of great value, right? So Orbital Insight is, doing things like urban development, where are the roads, where are the vehicles. We have to think about what are the things that they're not providing, or the sensitive analytics that we need to invest in as a community that are not going to be things that we could just buy, right? So there's some interesting discussion there. What are the particular layers that we can probably only provide ourselves because there's no economic incentive to do so. There's a lot of amazing work in doing things like semantic segmentation, where they're using things like SpaceNet, the equivalent of ImageNet, but for overhead. But we need more data for this that's labeled, and this is an area we really need to invest more in. So you look at all this stuff and you think, gosh, this looks pretty good. Or can we all go home now? Is it all just a good story? We were all recently at CBR, and you could get the impression that life is pretty good in deep land, right? You've got all these students that are doing their classifiers, training their deep learning systems, and then going off and selling the startup and making millions. But there's still some hard challenges that I think we really need to address. In particular, to our community over here, I think there's some things that really require some dedicated research. One of them is the fact that the world has this kind of heavy tail distribution, right? So you have these few categories that are very common. And if you notice, the Google object recognition app is really great at these type of things. The car, chair, monitor. But there's only really a few of these where you have that, abundant number of examples. A lot of the time we're interested in things that we only have a few handful of examples, these rare targets, or maybe some things that you've never even seen ever. So those are the type of challenges. And again, I think Anthony said this really nicely yesterday, was that, we should focus on the things that not everyone else is already funding. So this is one area where I think there is promising work in few-shot and zero-shot learning, but we need more. So just to illustrate this example, there's some amazing work out there where we'll take an image and it'll basically spit out a sentence, a full sentence description. And you give it images like this from the internet, it's like, my gosh, looks like it's a solved problem. It says a car parked next to the road. Okay, I'll give it that. It seems pretty close. When you realize, though, when you just type car into Google, this is the most common thing. Cars next to, basically parked on the sidewalk. So really, these approaches are great for the most common of scenes. As soon as you give it something a little bit strange, you get some, pretty out of the ordinary results or predictions, which is you're seeing down here. Same goes for this one over here for things that it hasn't seen very often. They degrade not very gracefully. But so how do we deal with these instances where we have few examples on hand? Again, as I mentioned, the community is already starting to look into this. There's work in few-shot and zero-shot learning, but this is an area that I'm hoping that we could support some more. I won't dwell on this too much. This is everyone probably in the room knows the challenges. This is the holy grail, how can we leverage unlabeled data? But I just wanted to point out that there is some incredibly very, very creative work of people of the community. There's a lot of folks are probably familiar with the kind of the generative adversarial approaches where they're saying, okay, I don't want to just learn how to classify the data. I actually want to be able to understand how to, from scratch, essentially say, paint me an image of a tank and really truly understand what that means. People mentioned synthetic data yesterday. I think that's another interesting intersection. How do we actually mix the work from kind of some of the generative approaches, synthetic data, and maybe a handful of real examples to create a strong classifier? There's also, I wanted to point out, this is, to me, very interesting work that's been happening where I think we could really leverage some of these ideas. The concept is, and we're just going through this right now in the Maven program, we're spending a considerable amount of money to label data. And in ImageNet, I said we had about 50,000 people working to label data. So we can't really expect that every new problem that we have in the IC, we're going to go off and have 50,000 people annotate data for us. So we need to get creative about how do we use our current data sets that actually might have hidden signals, supervisory signals, that we can actually use to train algorithms. Let me indicate what I mean by that. There's work, for example, that says I could potentially use the movement of the camera, for example, if I know some of those parameters as the label itself. So a lot of our sensors, we have a lot of metadata that could potentially be used as a surrogate for not necessarily having to have 50,000 people label this, we can actually potentially already leverage some of the metadata in our data sets to bootstrap some of these approaches. So that's something that I think could be very interesting for us to look at. The other thing that I think has also been mentioned is we have this incredible diversity in terms of the sensors that we have that doesn't have that much attention in the, say, CVPR community. There was this year a really great workshop at CVPR about computer vision beyond the visible spectrum, but I think there could be a lot more work that could be done in this area. Anthony mentioned this yesterday. I think there's the impression that you see these great results from ground level, and then that simply doesn't work usually for overhead, let alone for spectral. So again, there was a pretty great workshop as part of this year's CVPR. So another challenge that we face is deployment. So especially in DoD-IC, you can't expect to have, especially at the edge, you can't expect to have a supercomputer or a DGX-1 where you could just drop your deep learning system. So we need to get creative about we have this deep learning crank that people keep using, right? And the great thing is that it's very useful for a lot of things. You could say, okay, pass an image. Is it a car or a tank? You could even use things for semantic segmentation or even for overhead. But they're all using similar kind of convolutional based approaches. And the good news is that these things are getting better and better. But the bad news is that they're also very expensive in terms of computational. So this is about 20 billion flops of just for a forward pass to make an inference on one image. So these things are expensive, not just in terms of dollars, but also in terms of just memory and power. So there's a lot of interesting work that's been happening, and how do we optimize this to be able to deploy these systems at the edge? So there's work in having to do. I know you can't read this here, but this is essentially there's a lot of interesting work in having to say there's a lot of redundancy. Maybe we could compress some of these methods. There's a lot of work in having to do how can we improve the forward pass, and so there's a lot of good research that I think we should start incorporating. And the bottom line is that they really are starting to find a way to reduce both the compute and the power constraints for some of these approaches. What that allows us to do then is that you can start actually deploying these object recognition systems on fairly cheap hardware. This is me just showing that you can actually just, as a proof of concept, you could put this on a Raspberry Pi, So now, my family, which is very patient at me pointing, experiments at them, you'll notice now I'm able to, detect objects on this pretty much cheap hardware. And where it gets interesting is when you start incorporating this as part of platforms, right? So this here is just basically a little scary, but it's running just on a DJI drone, and it's just doing essentially object detection, and you can actually integrate that into the PID loop of the control of the actual platform. So now it could say, anytime I see a silver sedan, I'll follow it, or any other. And this is just running, now. I wish I could have brought it here. We can do an experiment. But so the other thing you could actually do is you could take it even smaller. This is actually what the drone sees. These are the different convolutional layers, and you're seeing the different kind of the output of the detection over here. That's kind of what's behind the scenes. You can actually really miniaturize these things, and this is where it gets very interesting. You could start. It's a balance between how much recognition power do I need and how much power am I drawing from the device. So really reducing the swap has been an interesting area of research. The other area that I think we would be very interesting to put additional resources in is that, okay, you're able to tell me that there's a car in this scene, but I think Anthony mentioned this again. Also, we need more work in complex activities and events. This is something that's we need more data. We need we need additional research in this area, because it's not going to work to just pass it through a convolutional neural net and just say vehicle and be done with it. I think one of the things, as a computer vision person, I got excited at one point when there was a bunch of analysts that we were working with, and we said, here's some video, and here's all these bounding boxes. We basically created another problem, right? So we really need to, that doesn't solve anything. So how do we actually start modeling some of these complex events and activities? And then we also, if we're going to be using these things at scale, we need to think about assurance and what are the things that essentially, for the longest time, nothing worked, so we really didn't think about security. So now that these things are actually beginning to get robust, we need to start thinking about counter AI seriously. And there is obviously a community that's been looking at this, and I'm hoping we can embrace the research they've been doing. Here I show here's a particular example. One of the recent excuse me, one of the recent papers is universal adversarial perturbations, and essentially you could think about it as an Instagram filter on an image that now at this point makes it not being able to recognize by a computer vision algorithm. You could even print that example, and what you're seeing on the right is completely wrong labels that the system is now fooled by that simple kind of Instagram filter. So, I think Ramachalapa mentioned yesterday, how do we think about noise, and how do we, in the training process, this is important for us to embrace and really think about it from a theoretical level. Because there's all kinds of things you can achieve with these adversarial approaches. You could do everything from just simple misclassification, but you could also do things like extract the training data, for example, and even extract the model. So we need to think about this carefully from an operational security, but also just from an assurance perspective. So in conclusion, I think it's an incredibly exciting time to be doing work in this area. I think we have some very unique, interesting research challenges. So I'm hoping we could find a way to harness the creativity and the work of the broader AI community, and how do we get them to help us with our problems. There's some particular things that I think that we should maybe foster and focus on, things like rare targets, our unique modalities. So I'm interested to hear your thoughts on some of this. Thank you very much for your time.
Thank you. If only you had listened to Jan LeCun as much as you had listened to Joe and Anthony yesterday, your career would have taken a totally different turn. Now, the reason why computer vision researchers were not into deep networks in the late 90s is because of the example, right? I thought about it a lot. MNIST is not something that vision people were interested in. We were just going into 3D at that time. Recovering 3D, representing 3D, and so on. So OCR was seen as a solved problem in pattern recognition, document IU. So if only ImageNet were available at that time, and one of Jan's students had done what Alex did several decades later, I think, it would have been accepted. So that was one of the issues, right? Where the application is and whether we think that's not going to work for us. At that time, we could not have done that. So that's one thing. Anyway, nice talk. It was a good summary, and I'm impressed how much you remember of all the talks yesterday. I don't remember most of it, but that's okay. Yeah, no, very nice talk. Any other questions to Mikel? Please.
Devshana DOE. How much of some of these new architectures are being used in image processing? By that I mean, in a lot of the architectures that are being used for image processing are based on von Neumann architectures. With this non-von Neumann architecture, such as neuromorphic computing, there's huge benefits, not just in terms of energy, but also in terms of acceleration for image processing. How much of that is being exploited these days?
Yeah, there's first of all, there's a lot of interesting work in other architectures. Neuromorphic is one of the ones that is in the timeline. But I like the phrase people have been using yesterday is about we're all participating in this great deep learning hackathon, and there are what I mentioned mostly today is what works the most, which is the convolutional neural net, deep convolutional neural net approaches. But there's also other very exotic architectures that are that people are employing. But from the hardware side, yeah, there's also embedded GPUs that are looking at particularly constrained like power environments. But and there's the whole wild west of the neuromorphic stuff, which is yet to really materialize, but is exciting to follow. But yeah, it's going to be. I think it's right now it's. An interesting time because this is kind of working, but we need to go back to some of these basics and say, well, if we're really optimizing for some of these things, how would we actually build this? And so it's
Anthony Hoogs, really a follow-up comment maybe on that question. And in the talk so far, we haven't really touched upon the contributions of deep learning and CNNs to image processing as opposed to, say, computer vision. But there are tremendous contributions and utility for CNNs, deep networks in this area. They've made huge strides in things like super resolution and all kinds of image sharpening, image enhancement, image transformations. And this is because the first few layers of the networks are learning signal processing basis, just like we used to hand design. A Gabor filter bank that was hand designed is now automatically learned by these networks, and it can be learned for your problem. So it's not necessarily a Gabor filter bank, it's an optimized filter bank that's going to address what you're trying to do. So for this community, in the IC, if you look at space imaging, you always want more resolution. There's really good ways to do super resolution now that are much better using deep networks than before. There's much better ways to do various forms of image cleanup. Colorization was one of them. You cited Alyosha Efros's work at Berkeley. He's working with us, my company Kitware, on the media forensics program at DARPA to look at this colorization problem and can you use that to detect that an image has been manipulated at the signal level. And they had some really nice work to detect image cropping. Was an image part of a crop or not? And you can do this with a neural network, it turns out, quite accurately. We don't really know how it works. We don't even know what it's actually doing, this neural network. But we think it's looking at the slight chromatic aberration that comes from the misalignment of pixels as you move away from the center projection of an image. You get a slight distortion in the RGB alignment of pixels across an image, and this is regardless of the content of the image and what it's showing. And so the CNN appears to be learning this. These tiny chromatic aberrations of where in an image the crop was taken from. A crop is a window of an image. So it's amazing what these things can learn even at that signal level, and they're still using standard architectures to do that. And this community has a number of specific problems in that area that we could potentially invest in.
Yeah. So my comments are motivated from the security side. A very interesting talk, and the one chart that really resonated with me was the chart that you talked about, the long tails for images. Now, if you I don't know if you can bring that chart back, but one of the things that I connect there from a security perspective is, how you go in two different dimensions. So if you go in the horizontal dimension, you talked about how the IC community has very specialized images. That's really also the point that came up yesterday, that in the security space we have very little ground truth. What's the next piece of malware going to look like, what it's going to do. And so very curious to know what kind of approaches you can take when the number of images or the ground truth is very small. And that how does deep learning evolve? I mean, so one of the approaches we are taking is we can't profile the ground truth, so we have to profile what is normal activity and then flag what's anomalous. Now that may work for some time, but how do we push that forward? The other part, if you go in the other dimension, which is the vertical dimension of your graph, you're showing the accuracy rates and so on. But these accuracy rates are against certain parameters for image recognition, which are essentially very brittle. And where you have to grow that is, exactly as you said, move the car up, it's no longer part of the road. Malware, you make slight mutations, slight variants, and now, in fact, 2 weeks ago at DEF CON, which is, I suppose you guys know, it's one of the premier security practitioners get together, white hats, black hats, and so on. They're trying to use neural networks to actually train to synthesize malware and evolve it in a way that would evade current antivirus engines. And that's part of AI and counter AI. So we have to think a little bit. I understand there's a huge revolution with image recognition and so on, but I think we have to abstract that away and say, okay, what does this mean for the more general problems around security? And I think that chart was very appropriate for that. So I'm going to end with one question, which is counter AI. I mean, I know you touched upon that, and counter AI assurance. Can you talk exactly, I mean, what are you seeing is happening in this space? Because what's clear is adversaries are using AI techniques and AI tools for synthesizing new variants of malware that's going to evade security controls. And we can't put ITAR-like restrictions on AI. Everybody can use, either TensorFlow or Caffe or Theano and so on. So all that stuff is out there. Adversaries are using it. So what's happening in counter AI? Is that something you could talk to?
Sure. mentioned briefly, it is an area where there's tremendous amount of work being done. So I completely sympathize with your comments. But there is both on the offensive side, defensive side. This is obviously a cat and mouse game. But there is some strong work that's coming out where people are saying, well, in our training, we really need to pay attention to the fact that people are going to be trying to mess with this, right? So there is from the defensive side, there's some really good work in adversarial training. But there's also, it's tremendous. I think it's important for us to recognize what's possible. I mean, it's really shocking to see that if you have a model out there and you've trained it on some data, it's very easy for people to extrapolate the data that you trained it on. What is the model itself? So being clear about that as a community of what's possible, I think will help us kind of in the operational security side of things. And also, I think there's some areas that there's not as much work because there's no economic incentives necessarily per se to work in that area, right? So we need to recognize those pockets and those gaps and really and fund research in those areas. So there is already a community that's been looking at this significantly, but I think there are some gaps that we can address.
Any other questions? Yeah, please.
Pelayo Fernandez says so. Question is that how useful might be synthetic data, such as gamers are realistically creating the world around us, and that might lend itself to helping CNNs and deep learning activities and algorithms learn better varieties of targets as opposed to having to worry about having a bunch of labelers. And I'm not sure how valid that approach might be and what the strengths and weaknesses are of using synthetic data from like gaming.
So yeah, there's a long history of using, or at least trying to use synthetic data in computer vision, right? So it's always been a balance between how do you make something so it's not a toy within that world. But I think there's some promising work that's being done right now where you want to essentially, OpenAI does this all the time, but so does a lot of the folks in the computer vision community. Essentially, you could bootstrap your approaches by having, a big synthetic world. And Anthony mentioned this a little bit. They're using DeerSig. You could do similar for overhead. So this is something that's emerging, but it's a tricky balance because at least from the work that we've done, you can't over rely on that. There's something about the world that's just very hard to capture in some of these simulations. So it's a tricky balance between how do we incorporate that to alleviate some of the labeling efforts, but it's something that I don't know if we've actually cracked yet. Yeah.
Sorry. Just a follow-up on that real quick. I think the combination of synthetic data plus adversarial networks could be really powerful because adversarial networks are really, they're typically used to generate data in a way that then can't be fooled by one of these adversarial attacks. And you could do that with synthetic data generation. You could generate synthetic data and then add noise or other things to make it look realistic, and you could learn how to make it look realistic automatically, so that it now can't be fooled or distinguished from the real data. So we have some funding now to try this in the next few months using DeerSig as the generator. So that's going to be quite interesting and exciting. And back to the gaming community, it turns out that the gaming community has, and I'm not a gamer, so excuse me if I'm wrong on this, there's probably some serious gamers in the room, but they've created all these 3D models of Russian military equipment. Hundreds and hundreds of these models, and they're openly available, 3D models with material attribution and so on for rendering. And so that's what the DeerSig people use. So they have these great models to render all this Russian military stuff that we might see in satellite imagery, and a bunch of Chinese stuff too, but it's really the Russian stuff that apparently is really popular.
Anthony, they may be fake models.
They might be.
Ellen Voorhees for the NIST. I just also wanted to comment on the synthetic data.
Press the microphone.
There we go. Sorry. My experience at NIST, we run a lot of evaluations and gather lots of data. My experience with data is, especially in a environment in where you're going to be using deep learning, that's the synthetic data has been generated by an algorithm. And what your systems are going to learn is what the algorithm was that generated that data. And to the extent that your data actually matches the real world, that will be okay. But in my experience, it just doesn't. Right? There are always things about the real world and the problem that you're trying to solve in that real world that your synthetic data is not going to capture. because it's not real.
Okay. Any other questions, comments? Yeah, please.
Kathy McEwen, Columbia University. I'm curious, we always come back to this question in various programs that I've been in with IARPA and DARPA, which is the communication or interaction with the intelligence community and how we can be informed by analysts, what their current practices are. And I'm wondering here with data, and particularly as we go into a multimodal stage where we're going to look at multimodal data, whether there is the captioning one is a good example. And when you had the picture of the tank, and we have very little of this, I'm sure that there's a lot of this. And I don't know, what is classified and could be released, but might there be cases where there are both images with accompanying text, which might be reports, which I think that would be great data to use to begin to talk about interaction between the text and the image for generating captions or generating descriptions, so forth.
So there was a good study that came out of DNI, a major issue study that I think addressed exactly that. We have on different networks, exactly as you said, descriptions and of an image, and why not harness that to power some of these approaches? And unfortunately, one of the things that we've had a challenge is some of these things are all just in different silos of data that don't talk to each other, and we don't usually think of harnessing those, say, analyst reports to drive, an AI system. So I think that your comment is well taken. I think that's something that we should start thinking about. And then the other challenge is how do we, some of these things are sensitive, so how do we still tap into the broader? We don't want to do this in isolation. There's some amazing ideas out in the academic community and industry. So how do we still provide data sets that are relevant and it can help us out is a challenge that but yeah.
Ramachalapa, the data issue is, I think, improving. I don't think we can get the restricted data because universities won't even touch ITAR data. But if you look at one of the projects we are involved in, and the one that Anthony and I will be involved in from IARPA, one is the Janus program, and we got a lot of data from the internet for face, but it's a very specific problem, face. For action recognition also, I think the data set is getting better. But some sensitive data just won't be available. That's always been a challenge. Even when all three of us were involved in a project known as Radius in the early 90s, we were working with model board imagery, very, very synthetic, like a little town, with buildings and little toy cars and so on, because national imagery could not be released outside. And I think synthetic data has its faults, but as long as we understand where the limitations are and not assume that, I think we are now in a period where we can't assume anything is real in some sense, right? Because there's so much flexibility for everybody else to go and change things. So we have to be careful,
I know we're getting close on time here, but yesterday Travis in the Maven presentation mentioned this treasure trove of data that the DoD and certainly the IC is sitting on. So part of that data is really what Kathy alluded to for at least the full motion video case for Predator Reaper type of video where there's cameras on UAVs. There's always a group of people watching that video in real time and logging about it. They're logging in a few different ways. There's what's called call-out text, and there's chat. Some of this is less structured, some of it's more structured, but it's always happening, and it's slightly stored in different silos, even within the enterprise of a given UAV system. But it is there. There's the call-out stuff is a little more structured, and it's meant to be more of a permanent record, and then the chat stuff looks like the text we saw yesterday. It's just text that's got a bunch of abbreviations. It has its own language issues. It's like its own dialect, effectively. But that data's there, and it's there for literally hundreds of thousands of hours of UAV video. Wouldn't that be awesome to take this data and try to use it? Because it's now video and captioning. Right? It's not all the things that are happening. It's the ones of intelligence interest. A lot of stuff. There was anything going on. but it's there, and there's a huge amount of it, and it could be leveraged in principle. So that's Maven's problem, right?